This is an image of a human temporal bone, and you can appreciate the auricle here and the spiraling cochlea. This is a small organ. It's encased in the hardest bone in the body. As you can see, it's surrounded by more bone. For all these reasons, clinical imaging of the inner ear today is not good enough to reveal cellular level pathology within the inner ear. You can see on the left a computed tomography scan, which is based on ionizing radiation, and on the right, a magnetic resonance imaging scan. And in both cases, the fluid-filled spaces are clearly seen. On the right, you can see them as bright signal. And on the left, you can see that the bone surrounding the cochlea is white. So all we know about the cellular origins of human hearing loss today comes from studying autopsy specimens when people die of unrelated causes and generously donate their ears for study. So then, through a laborious process that entails decalcification of the bone, embedding and sectioning, we can generate sections that look like this. And this is a human cochlea shown next to a penny. And you can appreciate that the size of the human cochlea is comparable to Lincoln's upper face on a penny. We have had to look into alternative ways that provide higher resolution, and one of them is micro-optical coherence tomography, which is a high-resolution successor of optical coherence tomography, which is a technique that's routinely used to diagnose retinal diseases in ophthalmology clinics across the world. So the first step was to use a micro-optical coherence tomography setup to compare a normal mouse cochlea on the top versus the ear that was exposed to loud noise for a couple of hours, the equivalent of attending a loud music concert. And you can see a striking difference where the organ of Corti is completely wiped out at the bottom. And this has really dramatic implications for therapy because numerous studies have shown that gene therapy doesn't work if there are no cells to treat. And these findings have inspired our many years of research to develop an imaging probe that can be inserted through the human inner ear through the round window, which is the natural opening into the inner ear, just the way we insert a cochlear implant. And here we demonstrate the feasibility of seeing the microstructure inside the cochlea, where the probe is inserted into the scala tympani, and you can see the organ of Corti and the surrounding microanatomy. We are eager to move the testing of this device into clinical trials. And in the meantime, we are developing a next generation successor of this probe that would provide even higher resolution, where we can really see individual cells and not only detect their structure, but also function. And this is called dynamic micro-optical coherence tomography. And by the way, the probe that we are inserting into the human inner ears in cadavers at this point is very small in diameter, the equivalent of 10 human hairs, and provides the resolution that's 100-fold higher than what's currently available.